Hey everyone, I'm Arvind and this is Easwar.
Hey.
We both are software engineers on the gRPC team at Google. We work on building new features, fixing bugs, and answering questions posted by our external users.
What is gRPC? But before that, what is an RPC? An RPC, or a remote procedure call, is a way for one program to call a function that gets executed on another program. The called function might execute in a different process on the same machine or on a different machine reachable via the network. At this point, we're going to assume that folks here have at least a high level conceptual understanding of what an RPC is. If you've seen a sequence diagram that looks something like this, or if you understand what is happening here, then you're good to go. If not, it might be a good idea to pause this video here, familiarize yourself with RPCs, and come back.
gRPC is a modern, high performance, cloud native RPC framework. What that means is gRPC is general purpose, can be run on Linux, Windows, Mac OS, Android, iOS, etc. Also supports x86 and ARM architectures. gRPC can be run on a server, on a mobile device, in the browser, and also on embedded systems. gRPC is language agnostic. This is the core essence of gRPC. We support C, C++, Go, Java, Python, Node, C Sharp, to name a few. gRPC is open source software and is accepted to Cloud Native Computing Foundation since 2017. gRPC has been built to power use cases to the last mile of computing. It relies on HTTP2 for the transport and uses protobufs as the interface definition language. This results in services where the APIs are well defined and the communication between the services are of low latency and high performance. Google has had an internal RPC framework called Stubby for decades. Stubby is being used at a planet scale for communication between services in different data centers. In 2015, Google decided to build the next version of Stubby and also make it open source. The result was gRPC. gRPC is production ready and is widely used within Google and in the industry. Further we go any further, Isha will let us know about these two technologies that form the foundation of gRPC.
HTTP2 started as a project named Speedy, whose motivation was a faster web. HTTP2's performance gains can be put down to three major things. Requests and responses are transmitted in binary format. Different request and response messages can be multiplexed on a single connection. Headers are compressed by default using HPAC. gRPC uses HTTP2 as its transport. What this means is that gRPC requests and responses are transmitted as HTTP2 frames. Protocol buffers, or protobufs, is an open source project for serializing structured data. You can think of it as being similar to XML or JSON, but faster, smaller, and simpler. Protobuf supports an interface definition language, or IDL, that allows developers to define the contract between the client and the server. This contract not only includes the methods exposed by the server, it also includes the structure of the request and response messages exchanged between the client and the server. The Protobuf IDL is strongly typed and supports forwards and backwards compatibility. This is key to be able to perform staged rollouts on your fleet of microservices. Protobuf supports tools to generate client and server-side code from this IDL for multiple programming languages. This allows developers to write services in their language of choice and still be able to interop with other services. Protobuf also ships with runtime libraries which perform serialization and deserialization. These are highly optimized for performance. Now that we've seen what gRPC is and what it's built on top of, Arvind will get us started with building a microservices-based application using gRPC.
Now imagine this pizza place in Sunnyvale, California. But they are in need of an online order processing application that needs to be accessible via mobile and desktop. Microservices has been around for a while. Microservices based architecture comes with a ton of advantages, but also comes with its own challenges, especially when it comes to service communication. gRPC was built with microservices in mind. In the next few slides, we will show you how we can build an application as a set of microservices that communicate with each other using gRPC. As software developers, we always want to see that beautiful system design diagram. Let us start by splitting the app into microservices and designing the role of each service. The order management service is the user-facing component and will support an API to order a pizza and to track the status of an order. The inventory service checks if an order can be satisfied based on the current stock. The payment service helps process user payments. The processing service manages the life cycle of an order. Now, Isha will take us through how to start by building the API contract using protofiles and how we can generate code and link our server/client to the system.
Protobuf allows you to define the contract between the client and the server. Here, we've defined the API to place an order for a pizza. The name of the RPC method is placeOrder. It takes a request message of type order request and returns a response message of type order response. Request and response messages are types themselves that allow you to group any number of fields in them. This RPC is an example of a unary RPC which is used for simple request and response scenarios. We will look at other RPC types later on in this video. The order request message contains fields to describe the order. We've defined fields to represent the size of the pizza, the toppings that go on top of it, and the customer making the order. The order response message contains the status of the order and an ID to subsequently track the order. This is an example of how complex proto messages can be built by composing simpler ones. In a RESTful world, there are two ways to describe the contract between the client and the server: a human-readable document describing the API, or a YAML file using the OpenAPI spec. Both can get quite verbose. We tried writing a YAML spec for the placeOrder API, and it turned out to be over 300 lines. Now that we've defined our API in a proto file, it's time to compile it using the proto compiler. This is a single command to generate language bindings for both server and client in Go. Arvind will now show us what the generated code looks like and how to integrate it with your client and server application code.
The generated language bindings are actually quite readable. The most important takeaway from the generated code on the server side is that this interface contains methods corresponding to the methods defined in the service definition. Since we define only one method in our service, we get an interface with a single method here. The server application must provide the implementation for this method. It typically involves performing all the required business logic, which could include making gRPC calls to other services, and finally returning a result to the caller. Once we have the service implementation ready, we have to create a gRPC server instance, register our service with the gRPC server, and start serving. The generated language bindings on the client side define an interface that's similar to the one on the server side. It contains methods matching those defined in the service. The implementation for this service is also provided by the generated code, and we refer to this implementation as the client stub, which takes care of converting calls from the client application into RPCs. On the client side, the first thing the application would do is to create a gRPC channel. A gRPC channel represents a virtual connection to the server. Once a channel is created, the application needs to create the stub by calling the function provided by the generated code. Once the stub is created, making an RPC is as simple as invoking the corresponding method on the client stub. gRPC handles all the magic by serializing and shipping the request to the server. Once it receives a response from the server, it deserializes it and makes it available to the client application. Now that we have a better understanding of how to define the service in Protobuf syntax and how to generate language-specific bindings, let's switch back to our pizza application.
Let's see how a user request is handled end to end. User makes a placeOrder RPC call. to the order service, which, as part of its business logic, interacts with other services before returning a response to the user. It first makes an RPC call to the inventory service to check if an order can be satisfied with the current inventory. The inventory service API will typically be defined in its own .proto file. Here, the order service acts as a client of the inventory service, and therefore would use the client stub from the inventory service's generated code to make this RPC. The inventory service sends a response which indicates whether the order can be satisfied. Based on this response, the order service makes another RPC call, this time to the payment service to process the customer's payment. Like the inventory service, the payment service API will be defined in its own .proto file. Payment service sends a response containing the status of the payment. Finally, the order service makes an RPC to the processing service to dispatch the order. The processing service sends a response containing an ID to track the order. At any point during this sequence of RPCs, the order service might return an error to the user. For example, if the order could not be processed based on the current inventory or if the payment processing failed. But if everything went well, the order service returns a response back to the user that contains the ID of the order. All RPCs shown so far are unary RPCs, which are of the request response type. Arvind will now take us through other RPC types supported by gRPC.
We already looked at what a unary RPC looks like. It is simple and more similar to a typical REST call. There are other three types of RPCs. The first is where the client sends a single message to the server and the server returns a stream of messages as its response. This is called server streaming RPCs. The second type is where the client sends a stream of messages to the server as part of the request, and the server comes back with a single response. This is called client streaming RPCs. The last type is bidirectional streaming RPCs, where each side can send a stream of messages to the other side, independent of each other. Let's define a server streaming RPC to stream order status to the client. This RPC accepts a status request message as input and returns a stream of status response messages. The server application will send a new message on the stream whenever the status of the pizza order changes. The status request message is a simple message containing the order ID for tracking. The status response message contains the current status of the order. And since we have defined the stream order status RPC as a server streaming RPC, the client will receive status updates from the server until the server decides to close the stream. Let's look at the flow for the server streaming RPC. The user makes the RPC call to the order management service. The RPC returns a stream from which the client can read messages sent by the server. The order management service makes a streaming RPC call to processing service. The processing service returns a stream from which the order management service can read status updates and push the same onto the stream to the user. Now over to Easwar.
So far, we've seen how we can implement some unary and streaming RPCs. Developing and running a microservices-based application involves more than just making a few RPC calls. gRPC is built with microservices in mind and supports a ton of features. Some are listed here, but gRPC supports much more. Instead of going into the details of each of these features, what we want to emphasize here is that gRPC is extensible. Features in gRPC are typically supported through a plugin mechanism, which allows developers to bring their own implementation. gRPC typically ships with one or two sane default implementations for each of these features. For example, if we consider service discovery, gRPC ships with a DNS-based service discovery mechanism. But if you want to use a different service discovery mechanism in your mesh, gRPC's plugin mechanism enables you to bring your own service discovery implementation which caters to your needs. Similarly, if we consider load balancing, gRPC ships with a few simple load balancing policies. But you're free to bring your own load balancing policies. We have a ton of examples in each of our language repositories in GitHub, which go over these features. Be sure to check them out.
We'll be back with more videos, and always, thanks for watching.